let's go over an example of using decision analysis for public health policy making. So it's wintertime, the flu season. So you want to examine the strategy that's most cost effective at preventing the flu in patients who are either vaccinated with the flu vaccine or not vaccinated. And usually the flu season lasts 1 year. So we know that the time horizon of the decision analysis model will be for 1 year. And this is very important because we want to consider the probability and the cost and the expected value to be set at a 1 year time point. So let's assume that we're also making this model from the perspective of the healthcare perspective. So that means we're going to be specifically interested in how to invest the limited resources that's most interested in the treatment strategy that will be the most bang for the buck. In other words, which treatment strategy would be most cost effective in preventing the flu? Now, typically what happens in the flu season is that people get vaccinated, right? Or they don't get vaccinated. And if they don't get vaccinated, either they believe in more supportive care by themselves. So we're just going to say we're going to look at either to get a vaccine or not to get a vaccine. And so we're going to look at these two different events that can happen. So let's just focus on the no vaccine for now. So when we look at the no vaccine, what are some possible events that can happen? Well, they can either then stay, they can either just remain well, right? Then they would just either have a good immune response or they become ill. And if they were to become ill, what would happen? Well, because they didn't get the vaccine, they're going to either have to recover either slower and maybe at a longer pace and by themselves at home, because probably they either want to do more home remedy, which is probably the reason why they didn't get vaccinated to begin with, and then either they want to go see a doctor. So if they were to go see a doctor, then maybe it might speed up the recovery because they're not just recovering by themselves at home, they're getting some treatment. Or if it's unfortunate scenario, which is that even if they go see the doctor, maybe it's so severe that even just home remedy isn't a possibility, so they can become hospitalized. So these are all the events that can happen if they don't get vaccinated. So now let's look at the top part of our tree here. So if we do get vaccinated, what can happen? Well, the similar events can also happen again too. Now, the vaccine isn't 100% bulletproof, right? I mean, hopefully you do get well, and there's also some probability that you become ill. And if you do become ill, what would happen? Well, you would still go see a doctor, right? Or either you become ill or you just recover on your own. So those are a couple chance events that can happen. And what happens after you recover? Well, you recover then. But if you see a doctor, what can happen? Well, you can either recover at that point after you see a doctor, or in some cases you can be hospitalized. So we want to make the tree as balanced as possible, right? If you notice that the tree here, the branches on the lower branches of the tree, which is no vaccinated, has a very similar subtree, right? Compared to the one on top, which is fine because we want the tree to be balanced. And now let's fill in the endpoints in our tree here. So what happens if they get well? Well, that's the end of that event. If they recover, well, we'll say they recover at that point and then they get well. And so these would be our chance, the expected value at the end of each of these branches. So now that we have our tree pretty balanced now, and the way we decide to kind of incorporate which are the factors that are most important, which is getting well, ill, recover, or seeing a doctor, recover, or being hospitalized. Now, as a decision maker working with the different perspective, you want to make sure that these specific chance note is most important to the decision maker here, right? So, and because seeing a doctor, right, is important from a healthcare perspective because it's the cost of the healthcare system. So now let's look at this more closely. So what is missing here in this tree for us to make a more informed decision? Well, we know that we want probabilities, right? Because when we see chance nodes, which are represented in circles here, we know that we have to add probability. We see the triangle, the inverted triangle, at the end of each of these branches. We know that these are associated with expected value number, so we know we're missing that. And because we're looking at a healthcare perspective, they're probably interested in the dollars that's associated with each of these different events that can happen. So we're also looking at some dollars here. So let's go into diving more deeply into this model by incorporating the probabilities, and all of these chance nodes, right? We know that there's probability that has to be associated with these chance nodes, and the probability always have to equal to 1, right? So the sum of these probabilities here has to equal to 1, and that there is a cost to each of these different events, right? So there's a cost to getting vaccinated, and in this scenario, we're going to say that there's probably no cost of getting a vaccine, right? Because if you're not getting a vaccine, there's no cost to that, to the healthcare system. And is there a cost to getting well? Well, probably not, right? Is there a cost to becoming ill? Well, we're going to assume that maybe you need to take more medication because now that you're ill, in addition to the cost of getting a vaccine, right? So there's a cost maybe associated with getting ill. Seeing a doctor, well, there's probably a cost of that associated with going to see the doctor, the copay, and all the other medical expenditure that goes into that. And what about when you recover? Well, recovering, we're going to assume that there's no cost to that. And when you become hospitalized, there's probably is some cost to being hospitalized, right? A day or 2 days, nights in a hospital. So we've labeled where we know we want to put some dollars and probabilities. So again, we look at the bottom part of the tree. Becoming ill, yeah, probably there's a cost to that. Seeing a doctor, yes, probably cost of that. We're going to assume that there's no cost to recovery, and so there's going to be no cost to recovery here, and there's probably a cost to hospitalization. So now that we have our tree that that we drew here together, we have a better sense of what the tree will help us to visualize between the two different strategies, which is either to get vaccinated or not vaccinated. Now, using the software triage, which we'll go over in another lecture video or in-class video, is it will help you to create this tree through the software where you can assess the cost, the probability, and the expected events, right, the values of each of these triangle nodes, and roll it back so that you can decide which of these strategies is the most cost-effective, right? Because in this particular decision, we're looking at the most cost-effective strategy. So let's dive into this more deeply. Now that we've finished drawing our decision tree using pencil or pen on paper, let's dive into how it will look on the software using the triage. Here you can see that we have the nodes as square, which represent the decision, and the circle represents the chance node. This is very similar to what we just drew. Now let's look at how can we put data in here. So let's assume that I was able to get some information based on last year's flu season, and I was able to know that those that got vaccinated had some percentage of remaining well, and there's a percentage that remained ill even though they were vaccinated. And also those that were vaccinated, there was some probability that they remain well even though they didn't have the vaccine, and those that became ill because they didn't get vaccinated. Now, the tree is very similar to what we just had in the drawing that we just made together. The purpose of this is to highlight how probabilities and these different chance events can actually influence the outcome and therefore your decision. So let's assume now that I have some of this information here. Becoming ill. So as I circle here, and let's say based on data that you've gotten either from a previous clinical trial or historical data, that not getting vaccinated, you can still remain well about 70% of the time. And if it's 70% of the time you're well, if you're not vaccinated, you have about 30% of becoming ill. If you're only able to get information that related to only one of the chance nodes, such as if I'm not vaccinated, I have about a 30% chance of getting ill. Because the probabilities, the summation of the probabilities of the chance node has to equal to 1, you can infer that if you know that you have 30% of getting ill, therefore 1 minus 30% is equal to 70%. Therefore, you have a 70% of getting well if not vaccinated. So all this probability all have to equal to 1. All the probability here also have to equal to 1. So this is correct. I always like to do a probability check-in, just making sure all the decimals are in the right place. So let's say you have some more data that shows that if you would be vaccinated and to become ill, And what happens then? Well, there's a chance event that you can recover or see a doctor. And maybe based on historical data, you're able to show that you have 90% of recovering from becoming ill, and about 10% seeing a doctor if you're not recovered. And if you, after seeing a doctor, you have a really strong chance of recovering, almost 99.9%, and you have almost just a 0.1% of being hospitalized. So that's 0.001. So those are our probability. So now let's look at the bottom tree. So if we were to not get vaccinated and we become ill, we have about 80% of recovery and therefore 20% of seeing a doctor. If we were to see the doctor, we have about 99% of recovering, not 99.9, because since we weren't vaccinated, but that's still pretty good. And we have about 0.01, which is equal to 1% of being hospitalized. So these are the probabilities that we're going to input into our model. So now that we've input the probability in the model, let's look at costs. So let's say in this study, we know that the vaccine is going to cost around $10. So if that's the case, let's look at what the cost related to the different variables. So if you're not vaccinated, there's no cost to us, and the cost to be vaccinated is $10. And if you are well, which is good, there's no cost to the healthcare system, but if you become ill, there's a cost of $12. So let's say that we were able to get this information based on some historical data that shows that it'll cost about $12 to remain ill. That, for example, could include over-the-counter medication. So that's why we're counting the $12. So this may be related to the cost of medication, and so that's what we're going to look at here. So if we were to be recovered, right, from taking the over-the-counter medication and recover, there's zero cost in. But let's say we took the over-the-counter medication and we're still sick. Then we'll have to go see a doctor. And so let's say this is copay and maybe some stronger meds. So that's $110. So after $110, hopefully you recover, because why? Well, you have a pretty strong probability, right? And so if that's the case, then recovery is $0. Now, if let's say you don't recover, you are hospitalized, that's about $5,000. That might include inpatient stay, and 1 or 2 nights in a hospital, medication, specialists. We're just going to estimate $5,000. So now we covered the top part. Now let's look at the bottom part now here. Here, if we remain well, about $0, same thing as the one we see on the top. And here we're assuming that the medication, the over-the-counter medication, whether you're vaccinated or not vaccinated, is still $12, right? Because you're still sick. And if you were to recover, no dollars. And if you see a doctor, if you become ill, is $110. And if you were to recover, no dollars. And to be hospitalized, $5,000. So now we inputted the cost, and in our previous slide, we inputted the probability. We're almost halfway there of our tree. So what is missing? Well, we're missing the expected value at the end of each of the determiner node. So how do we determine this? Well, you determine the expected cost, or you can think of the expected value of each of these determiner nodes by taking the probability associated with that particular strategy, multiplying by the dollars. So in this case, let's say we're going to look at this first one on the top. Let's say vaccinated and getting well. So here we have 0.97, which is 97%, right, times the $10, and that will give us $9.70. So that is the expected value of this whole strategy here. Now let's do the same for the second one. So the expected value is equal to the summation of 0.9 and 0.03. So 0.9 times 0.03 is equal to 0.027. And 0.027 times the summation of $12 plus $10 is equal to $22. So in this specific expected value is 0.59 cents. or $0.59 or 59 cents. And so forth. We will do the same for the rest of the tree. So here, if you look at this part of the tree, how do we get this number? Well, this number, 0.002997, comes from multiplying 0.999 times 0.10 times 0.03. That gives you 0.002997. And then how do we get $132? That's the summation of 110 plus 12 plus 10 equals to 132. So now that is the total cost of this whole branch of this tree times the probability, the summation of the probability, right, which is 0.002997, and that gives us 0.40, which is 40 cents, or $0.40, and so forth. You would keep doing the same for each of the different terminal nodes by multiplying the summation of the cost and the summation of the probability. And that will give you the expected value of each of these terminal nodes. Since I went over this example on the top, why don't you try calculating this part? Take a few minutes, get out your calculator, and calculate the expected value for each of these different strategy of this decision tree. I hope that was fun. Hopefully you were able to calculate the expected value for each of these trees. So what do you do now? So now that you calculate the expected cost of each of the terminal nodes, right, that we see here, what you can do is you can then compare the two different strategies and determine which of these is most cost effective, because in this scenario, we're looking at most cost effective, right? So we want to see the strategy that has the smaller value, which would be the one that's most cost effective. If we were looking for which of the strategy will yield the highest profit, in that case, we will want to see the strategy that will yield the higher number. So depending upon what you're looking for, the strategies will be based on the decision maker's perspective and what the goals are. So the first strategy to determine which of the strategy is called the expected value summation. So now that you calculated the expected cost for each of the terminal nodes, let's say there's 4 here in the vaccinated strategy, you would put it on the table. This is a nice way to organize your thoughts. And you would add the summation, add this all together, so that at this strategy, this is $10.71. And which is the supportive arm, which is basically the no vaccinated arm, you would also do the same. Add the expected cost for the 4 different terminal node, and you would yield $13.12. So now, there's a second way to calculate the expected value for the 2 different strategy, and that is called the rollback method. The reason why we will also want to go over the rollback method is that in the triage software that we will be using, it will be based on this rollback method. So that's why I want to go over this. So you do the same thing which you've been doing, which is the calculation of the expected value for each of the different nodes, except for this time you're doing it one piece at a time. You're going to be rolling back from the back of the tree to the front. So what you see here is, let's say this is a summation of the cost of this node. We're going to take the cost of the node, multiply by the first immediate probability before that strategy at this particular node. And then we're also going to add the numerator, which is basically going to add this product plus the product of this, which is the $5,122 times 0.01. And this answer will give you $172. You will do the same for the denominator, which is the 0.99, times 0.0594, which is the n of the expected, which is the expected value probability here, multiply by the 0.99, and also you do the same, 0.006 times 0.01. And you would then add 0.0594 and 0.006, and that will give you 0.0588. So now that you have this expected value here, you would then compare this expected value and this expected value here. And now you do the same for this node. You work backwards, and you would do the same for the other decision, which is the vaccinated. So as you can see, you can determine the expected value of each of these nodes by doing the rollback. The answer should be the same that you get here on this table, which is $10.71 compared to $13.20. Even though the methods are different, which is this is a summation based on adding the expected costs compared to the different branches of your decision. And in this case, which is the second method, which is the rollback, which is then you're taking the terminal expected value and rolling it backwards until you get to the front. And this will also yield a similar number, which you will also see the same numbers here. But for this exercise, I would like you to take time to discover or calculate what are the determinant for A, B, C, D, and E. And whatever answer that you got between A and B, this will help determine which of the decision here, which is the vaccinated or not vaccinated, is most cost effective. So if we were to go back to this model and we were able to do the expected summation and determine that the total expected value of the vaccinated arm is $10.71 and the non-vaccinated, which is a supportive arm, is $13.20, we want to find which of the strategy is most cost effective. So are we going to look for the number that's smaller or bigger? Let's think about this. Most cost effective. So we want to see which of these is most cost saving. So the $10.71, right, is the smaller number compared to $13.20. So therefore, it is the vaccinated arm which is going to be considered more cost effective.